Welcome to today's paper reading. Today's paper is titled, RAG and RAU, a survey on Retrieval-Augmented Language Model and Natural Language Processing. This paper was published on the AR14 preprint by Yucheng Hu and Yuxing Liu from East China University of Science and Technology and Peking University. Large language models, LLMs, have made significant strides in natural language processing, NLP, but they face challenges such as hallucination and the need for domain-specific knowledge. To address these issues, recent methodologies have integrated external information retrieval with LLMs, significantly enhancing their performance. This survey paper provides a comprehensive overview of retrieval-augmented language models, RALMs, including retrieval-augmented generation, RAG, and retrieval-augmented understanding, RAU. The paper examines the essential components of RALMs, such as retrievers, language models, and augmentations, and how their interactions lead to diverse model structures and applications. RALMs are shown to be useful in a variety of tasks, from translation and dialogue systems to knowledge-intensive applications. The survey also discusses evaluation methods, emphasizing the importance of robustness, accuracy, and relevance. Additionally, it acknowledges the limitations of RALMs, particularly in retrieval quality and computational efficiency, and suggests directions for future research. Natural language processing, NLP, is a multidisciplinary field that integrates linguistics, computer science, and mathematics to enable effective communication between humans and computers using natural language. Traditional NLP tasks have employed statistic-based algorithms and deep learning algorithms such as CNNs and RNNs. Recently, the transformer architecture has become prominent, significantly enhancing performance in NLP tasks. However, current challenges include the hallucination phenomenon, limitations in handling knowledge-intensive tasks, and difficulties in promptly updating knowledge. These issues highlight the need for further research and development in NLP. Figure 1 provides a general overview of the framework of Retrieval-Augmented Language Model, RALM, methods. It highlights the essential components of RALMs, including retrievers and language models, and how their interactions lead to diverse model structures and applications. The figure also emphasizes the utility of RALMs in a spectrum of tasks, from translation and dialogue systems to knowledge-intensive applications. The basic architecture of the Retrieval-Augmented Language Model, RALM, is defined by the function y equals f, x, z, where z represents the retrieved message, x is the input, and y is the output. The model involves three main types of interactions: sequential single interaction, sequential multiple interactions, and parallel interaction. In sequential single interaction, the model finds the top k relevant documents z to input x to a retriever, and then the language model generates the ith token e. For sequential multiple interactions, the model refines the output of the language model with retrieved information over multiple steps. In parallel interaction, the retriever and the language model work independently on the input x, with the final output determined by a weighted interpolation function. Key equations include E equals LM z x year for a single interaction, ys equals LM z x, y less than s for multiple interactions, and y equals I LM x year z for parallel interaction. Figure 2 illustrates the three primary modes through which a retriever interacts with a language model, LM, within the context of retrieval-augmented language models, RALM. The first mode, sequential single interaction, involves the retriever first identifying the top k relevant documents based on the input, which are then passed to the LM for token generation. The second mode, sequential multiple interactions, addresses the limitations of single interactions by allowing multiple rounds of retrieval and LM processing, particularly useful for long dialogues and multi-hop problems. The third mode, parallel interaction, proposes a non-sequential approach where the retriever and LM operate independently on the input, with the final output being a weighted combination of their respective outputs. This figure provides a clear categorization of the interaction methods, highlighting their distinct operational structures and applications within RALM. In the RALM architecture, retrievers are crucial for improving the accuracy of language models. The retrieval methods are categorized into sparse retrieval, dense retrieval, internet retrieval, and hybrid retrieval. Sparse retrieval includes methods like TF-IDF and BM25, which are simple and effective, and sparse vector representation, which captures semantic essence. Dense retrieval involves techniques like word embedding, multimodal retrieval, and knowledge distillation, using deep learning to enhance accuracy. Internet retrieval leverages commercial search engines, while hybrid retrieval combines various techniques to improve robustness and effectiveness. Figure 3 provides a visual roadmap of the three main types of interactions within the Retrieval-Augmented Language Model (RALM) framework. The purple areas on the roadmap represent research and work focused on sequential interaction (RALM) models, where interactions follow a clear sequential order. The red boxes indicate areas of research dedicated to sequential multiple interactions (RALM) models, which involve multiple interactions to handle more complex tasks. Lastly, the yellow areas signify work on parallel interaction RALM models, where the retriever and language model operate independently and their outputs are combined through a weighted interpolation process. Table 1 provides a comprehensive summary of the various retrievers used in the Retrieval-Augmented Language Model (RALM) architecture. The retrievers are categorized into four main types: sparse retrieval, dense retrieval, internet retrieval, and hybrid retrieval. Each category includes specific techniques and references to the year of their application in RALM works. For instance, sparse retrieval techniques include BM25 and word embedding, while dense retrieval encompasses methods like KNN search and GR. Internet retrieval and hybrid retrieval also list their respective techniques and year references, showcasing the diversity and evolution of retrieval methods in RALM. In the context of RALM architectures, language models are categorized into three main types: autoencoder, autoregressive, and encoder-decoder models. Autoencoder language models, such as BERT, RoBERTa, and GPT 3.5, are designed to reconstruct input data by learning robust features, which is particularly useful for natural language understanding tasks. Autoregressive models, exemplified by the GPT family and Llama family, predict the next word in a sequence, making them suitable for generative tasks like dialogue generation and machine translation. Encoder-decoder models, including T5 and BART, utilize the transformer architecture to process entire text sequences in parallel, enhancing both training and inference speeds. Each type of model brings unique capabilities to the RALM framework, contributing to its versatility and effectiveness in various NLP tasks. Table 2 provides a comprehensive summary of the language models, LLMs, utilized in Retrieval-Augmented Language Models, RALM, methods. The table categorizes these models into three main types: autoencoder language models, autoregressive language models, and encoder-decoder language models. Notable models within these categories include RoBERTa, GPT-3, and T5, each with their respective year references indicating when they were introduced and utilized in RALM architectures. This table serves as a valuable resource for understanding the evolution and application of LLMs in enhancing RALM performance. The enhancement of the RALM architecture is divided into three main parts: retriever enhancement, LM enhancement, and overall enhancement. In retriever enhancement, the focus is on improving the quality and timing of retrievals, with notable methods like self-RAG and FILCO. LM enhancement involves optimizing the language model through pre-generation processing, structural adjustments, and post-generation output refinement. Finally, overall enhancement covers end-to-end training approaches and the introduction of intermediate modules to improve the overall system performance and domain adaptability. Figure 4 categorizes the enhancement methods for the RALM architecture into three main areas: retriever enhancement, LM enhancement, and overall enhancement. Under retriever enhancement, methods focus on improving the quality of retrieved documents and optimizing the timing of retrievals. LM enhancement involves processes before, during, and after the generation of language model outputs to improve their quality. Overall enhancement covers end-to-end training approaches and the construction of intermediate modules to coordinate retriever and language model activities. Figure 5 categorizes the data sources used in RALM into structured and unstructured data. Structured data includes knowledge graphs like Wikidata 5M and WikiKG90MV2, and structured text datasets such as Natural Questions, NQ, and HotPotQA, HQA. Unstructured data encompasses various forms like text from Fever, images from datasets like NIST and CIFAR-10, and multimedia formats including audio and video. This classification helps in understanding the diverse data types leveraged by RALM for various tasks. In the context of RALM, data sources are categorized into structured and unstructured data. Structured data includes well-defined formats like Natural Questions, NQ, HotPotQA, HQA, and knowledge graphs. These datasets are crucial for training models and enabling multi-hop question answering. On the other hand, unstructured data, such as text from Fever, images from datasets like NIST and COCO, and audio-video from LJ Speech and HMEB, provide diverse and rich information but require specialized processing techniques. Researchers like Wang et al., 2023c, and Katab et al., 2022, have extensively used these data sources to advance RALM applications. The RALM architecture is applied across various downstream tasks, categorized by whether they primarily require model generation or comprehension capabilities. For NLG tasks, RALM is used in machine translation, math teaching, and dialogue generation. In machine translation, systems like SelfMum and Trime have shown enhanced performance. Math teaching applications, such as Leave-Onion, use retrieval enhancement generation systems. Dialogue generation tasks, like those tackled by Philco and Surge, leverage datasets and knowledge graphs to improve dialogue quality. On the NLU side, RALM is employed in slot filling, image generation, and fact-checking. Slot filling, enhanced by systems like KGI, involves extracting specific information from text. Image generation models, such as RIMAGIN and RDM, focus on creating images from text descriptions. Fact-checking, exemplified by RAG and Atlas, verifies statements based on evidence. Finally, for tasks requiring both NLU and NLG capabilities, RALM is used in text summarization, question answering, and code generation. Text summarization models like RADIT and SelfMem generate concise summaries. Question answering systems, such as RAG and iChrome, retrieve and generate answers. Code generation and summarization, like Redcoder and Race, involve creating and summarizing computer program code. Figure 6 categorizes the applications of RALM into three main areas: NLG tasks, NLU tasks, and tasks requiring both NLU and NLG capabilities. NLG tasks include machine translation, math teaching, and dialogue generation, which focus on generating content. NLU tasks involve slot filling, image generation, and fact-checking, which require understanding and processing of natural language. Tasks that require both NLU and NLG capabilities include text summarization, question answering, and code generation, which involve both understanding and generating content. The evaluation of RALM involves several approaches and benchmarks. Initially, RAGAs used the WikiEval dataset to assess faithfulness, answer relevance, and context relevance. RGB developed a bilingual evaluation system with metrics like accuracy and error detection rate. CRUD-RAG focused on the impact of retrieval components and external knowledge bases. In specific domains, Recall tested RALM's susceptibility to inaccurate information using the Event KG and UJ datasets. Mirage, focused on the medical domain, evaluated zero-shot learning and retrieval-augmented generation. Aries employed a lightweight LM and human-labeled data for detailed component evaluation. Table 3 provides a comprehensive summary of various evaluation methods used in the context of retrieval-augmented language models, RALM. The table categorizes different evaluation techniques by their target metrics and datasets. For instance, RAGAS focuses on assessing the faithfulness, answer relevance, and context relevance of RALM outputs using the WikiEval dataset. RGB, on the other hand, evaluates noise robustness, negative rejection, and counterfactual robustness using a bilingual Chinese and English evaluation system. CRUD-RAG evaluates the quality of retrieval and generation through metrics like Rouge, BLEU, BERT score, and RAG Quest-Eval. This table is crucial for understanding the diverse ways in which RLM performance is measured and validated across different datasets and criteria. The discussion section of the paper focuses on the limitations of existing retrieval-augmented language models, RALMs, and potential future developments. Key limitations include poor robustness, where simple attacks can diminish relevance and accuracy, poor quality of retrieval results, due to variable internet source quality, and overspending, with extensive model changes and complex operations increasing time and space overhead. Future prospects involve improving model robustness through methods like gradient-guided prompt perturbation, GGPP, enhancing retrieval quality by refining datasets and improving retrieval techniques, and balancing expenses and benefits by designing plug-and-play modules and utilizing in-context learning. Additionally, the paper suggests expanding RLM applications to areas like decision support, search engines, and recommendation systems, leveraging RALM's strengths in knowledge and experience. Figure 7 outlines the key limitations of current retrieval-augmented language models, RALMs, and suggests potential future developments to address these issues. The primary limitations identified include poor robustness against adversarial inputs, variability in the quality of retrieval results, and high computational costs associated with model deployment and scalability. Future prospects focus on improving model robustness, enhancing retrieval quality, and exploring cost-effective solutions to maintain a balance between performance and efficiency. These advancements aim to leverage more sophisticated techniques and integrate RALMs with other AI technologies to address a broader spectrum of challenges. The integration of retrieval-augmented language models, RALMs, has significantly advanced the capabilities of NLP systems. RALMs enhance language models by retrieving and integrating external knowledge, leading to improved performance across various NLP tasks such as translation, dialogue generation, and knowledge graph completion. However, RALMs face several limitations, including robustness against adversarial inputs, the quality of retrieval results, and the computational costs associated with their deployment. Future advancements in RALMs will depend on enhancing their robustness, improving retrieval quality, and expanding their application scope. By incorporating more sophisticated techniques and integrating RALMs with other AI technologies, these models can address a broader spectrum of challenges, potentially enabling AI systems with deeper understanding and more human-like language capabilities. Thank you for watching.